what I would like to do today is we'll talk about water distribution system compliance monitoring. We'll talk a little bit about water distribution systems, and if we have time, we will set up the equations to show you how to calculate the Langelier saturation index that you'll calculate as part of the lab report. So when we're thinking about water quality, we need to think about what are the factors that affect water quality. And I've listed a number here. So for example, if we're looking at source water, we can talk about fresh water. We can talk about seawater and desalinate. We can talk about water that is soft, so groundwater. Generally surface water. We can also have groundwaters that are soft. We can talk about groundwaters that are very hard, that have a high mineral content. We can talk about water that has a high organic matter content. And these impact how we treat water, and they also impact the quality of that water. So for example, if we have water that has a high NOM, we chlorinate that water, there is the potential for high concentrations of the various disinfection byproducts. We also talk about water age. So water age is the time that it takes for the water to leave, from the time it leaves the plant to the time that it reaches your home. Now that can range anywhere from a few hours if you're very close to the water treatment plant. It can be days. It can be 48 hours, 2 days. It can be up 5 or even longer. This plays a significant role because the longer that the water is in the pipes, the longer time for reactions to occur. So for instance, we just mentioned NOM and the formation of potential byproducts. Well, the longer that water is in the piping network, the greater the opportunity for disinfection byproducts to form. The other possibility is that the disinfectant, often we're using chlorine as the disinfectant, that chlorine reacts in the distribution system, and the longer the water age, the more that it degrades and the lower the concentration in at the tap. We also talk about water treatment and water chemistry. Those of you that are in 483, this week we're talking about coagulation. Mentioned, and as we'll look at in the problem this week, adding a coagulant consumes alkalinity. So if we consume alkalinity, and alkalinity is the ability of a water to resist a pH change upon the addition of an acid. So if we reduce the alkalinity, that can result in pH swings. So we can end up significant changes in alkalinity. We can have either pH increases, we can have pH decreases, depending on the treatment that is used. Temperature plays an important role. So the greater the temperature, as temperature increases, microbial growth increases, and we can have the production of biofilms. Those biofilms can harbor various different organisms, including pathogenic organisms like Legionella, and that can cause human disease. Also, as temperature increases, chlorine decay also increases, so the rate increases. Mentioned biofilm formation in terms of here, but also, again, if we have biofilm formation, the organism Legionella can proliferate. Legionella is pathogenic, it's inhaled, it causes pneumonia. And obviously that is a problem. The condition of the distribution system is an issue. Do we have leaks? Are they leaks in the major piping network where soil bacteria can actually enter the distribution system? Or do we have, you'll see pictures of it, what we call tubercles formed, or turbulation, and there you end up with basically rust on the inside of an iron pipe. That rust can slough off and you end up with red water. And the distribution materials also play a significant role. Common distribution materials, PVC, copper. Common previously was lead, galvanized. Let's see, what else? Cast iron. So various different types, and they will play a significant role in water quality. Now we need to define what is a public water system. So my goal is to help you get to the point where you can design a sampling strategy and actually go out and collect the samples. So public water supply, it's any system serving 15 or more connections or an average of 25 or more people per day for at least 60 days per year. And these are categorized as either a community water supply. So obviously, if you're in East Lansing, Meridian Township, the East Lansing Meridian Township is a community water system. If you're in Lansing, Board of Water and Light, it's a community water system. What about MSU? Is MSU a community water system? MSU is classified as a community water system. It provides water to a residential community essentially year-round. A non-transient, non-community water system is a system that supplies water, again, to at least 25 of the same people at least 6 months of the year, but not to their residences. So the issue is that MSU is providing water to those of you that are residing on campus. So therefore, it's considered a community water supply. Community, non-community water supply could be a school, but one that has its own supply, but students aren't living there. Could be a factory. Could be hospitals. A transient non-community water supply supplies water where people don't remain in that location for long periods of time. So this is, for instance, a campground, a rest stop. No one is residing in a rest stop, hopefully, and a campground. Yes, they're there, but only for a short period of time. Now, we want to make sure that the water that is supplied is what we refer to as safe. Now, safe, we could debate a lot about what that really means. For the sake of the argument here, we're talking about compliant with regulation. So we're really focused on environmental regulatory compliance. And these community water systems are charged with 4 responsibilities. 1, meeting all of the safe drinking water standards. And these are promulgated by the US EPA and by the state agency that has primacy. So in Michigan, that is EGLE. The MCLs are the maximum contaminant levels. So these, for instance, include chemicals like bromate, which is actually a disinfection byproduct, which is set at 10 micrograms per liter. They also include what are referred to as treatment technology regulations. And these are set in a way that the treatment itself is what is regulated, in part because it's in many cases, it's too difficult to monitor for the chemical itself. So for example, for cryptosporidium, which is a protozoan parasite, or for viruses, very difficult for a small water system to actually culture. There we use what is referred to as the CT concept. And those of you in 483 have taken 483 or will take 483, we will talk about what that CT concept means. Lead and copper is regulated by the lead and copper rule. It's a treatment technology regulation. We don't have a health-based standard for lead. We do not have a health-based standard for copper. Now, community water systems are run by certified operators. MSU has a certified operator. They're certified by the state. They have to meet certain requirements for education, for experience. They have to take a test. The test varies, and the education and research requirements vary depending on the type of certification they have. And the person that's in charge at the plant is referred to as the OIC, or the operator in charge. Now that operator is responsible not only for ensuring that the water meets all of the regulations, but also devising a sampling plan. And that sampling plan includes where samples are taken, when they are taken, how they are taken, how they are stored, how they are logged into the system, how they are analyzed, how they are reported, and how those reports are maintained. Failing to do any of that is a violation and actually can result in loss of certification. And yes, that does happen. So records have to be kept, and they have to be kept for a particular period of time, depending on the type of records. So for instance, bacteriological records have to be kept for 5 years. Violation corrective actions have to be kept for 3 years. So those are all codified in the federal regulations, so in the CFR and also in the state rules. And the state rules can be more stringent than the federal regulations, but they cannot be more lax. Also require sanitary survey reports, and those provide an opportunity for the primacy agency. So in the case of Michigan, that is EGLE, to visit the system, speak with the operators, if necessary, educate the operators about proper monitoring and sampling procedures, and also to provide technical assistance. So there are district engineers in Michigan in each of the districts, and those district engineers regularly visit each of the treatment facilities. So it's meant to be a proactive public health measure to ensure that the water that is distributed meets all of the regulations, is wholesome, is palatable, so it is pleasing, and potable, safe to drink. Now, The consumer confidence reports are required by the US EPA, and these are annual reports that every system must generate, must provide to its customers. And these identify the source of the water, what's in the water, specific requirements, what they have to provide in terms of that information. Also talks about what you can do to protect your water source, lists any violations that occurred in the past year, any health risks, discusses how those violations were corrected, outlines any projects that are planned for the system, and it has to be sent by July 1 every year. So Michigan State produces and provides a consumer confidence report or a water quality report every year. If you search MSU water quality report, you will find that water quality report, and you will have to actually find it for the first lab. This is just an example of the water quality report from Detroit. And notice it has certain requirements for what providing information about water at the tap. And what's required also depends whether it's a groundwater source or a surface water source. The regulations for surface water are much more stringent than that for groundwater. And notice it's providing information about turbidity from the filters. And there are specific requirements about turbidity levels. It also provides information about inorganics. So for instance, it has information about fluoride and when it was sampled, the MCL which is 4, and the highest level that is detected, which was 0.8. So you can see that it is significantly less than the MCL, and the range that was detected is 0.63 to 0.8. So there's no violation. Same with nitrate, that's also provided. Barium is also provided. What is required will vary. So in terms of some of the common water quality parameters that are measured include, we've mentioned some of these, various disinfectants. So these include trihalomethane, so chloroform, bromoform, haloacetic acids, bromate. It includes microbials. Notice viruses are not measured. What are required to be measured are total coliform and E. coli. And if you're not monitoring that, then you have to monitor heterotrophic bacteria. There are requirements for a number of chemicals and requirements for physical parameters such as turbidity, color, taste and odor, pressure. Why do we monitor pressure? Why do we care about pressure in the distribution system? To ensure no backflow. To ensure that if the system is pressurized, we don't have backflow, we're less likely to have infiltration. If we have a leak in the pipe, we would, from the health perspective, it's better to have water flowing from that pipe rather than into that pipe. The water quality report or the consumer confidence reports also will talk about the wellhead protection program for groundwater supplies. Look at the MSU one, talks about wellhead protection. What is done to ensure that the groundwater quality doesn't deteriorate? So every system that is a groundwater system has to assess the hydrology of the wellhead zone. They need to perform a risk assessment. They need to know where underground storage tanks are located. They need to ensure that there's not contamination of wells in the vicinity of those underground storage tanks. They need to be concerned with both urban and agricultural runoff. In studies looking at groundwater quality in Michigan, one of the things that we're seeing is, and it's actually done in Ingham County, is increased levels of chloride. What are the potential sources of that chloride in the groundwater? Why might chloride levels be increasing in Michigan in groundwater? And actually also in surface water, but talking about groundwater. We salt the roads. Exactly. Runoff from road salt. So if that can infiltrate, for instance, in a recharge zone, that gets into the aquifer, and that can increase the concentration of chloride in the aquifer. Upwelling, because Michigan is a seabed, and upwelling of chloride from deep in the much deeper aquifers can also occur. We also monitor surface water. Again, because we're concerned with what those contaminants are in the surface water and how they're impacting water quality and therefore the treatment that's needed. Now, this is a schematic of a distribution system. So let's start, okay, we've got, in this case, a source water. So water's pumped from that source water to the treatment plant. Chemicals are added, water quality is improved, and then it is sent out into the larger mains known as distribution or transmission mains. It continues. There are trunk mains. So this may be, for instance, Lansing Board of Water and Light sells water to DeWitt Township. So DeWitt Township is purchasing water from Detroit Water and Sewer. The East Lansing Meridian Township Water Authority is the treatment. East Lansing purchases water from that utility, same also Meridian Township. So there was trunk main. There may be a storage reservoir. Get more trunk mains. Now we're moving out into the distribution mains, and we move out eventually to what we refer to as the service line. So you can see, it's a large system. It may be hundreds of miles of pipeline from the time that that water is treated to actually when it gets to the home. So I mentioned disinfection byproducts. Okay. These are regulated under what is referred to as the disinfection byproduct rule. And there are maximum residual disinfectant goals and levels. So the levels are mandated and they're enforceable. Goals are not enforceable. And there are levels for 3 disinfectants: chlorine, chloramine, and chlorine dioxide. And then there are maximum contaminant level goals and maximum contaminant levels for what we refer to as total trihalomethanes. So that's THM. So that includes chloroform, bromo dichloromethane, dibromochloromethane, and bromoform. And the haloacetic acids, there are 5 that are regulated: chlorite, which is toxic, and bromate, which is a carcinogen. So bromate is formed from the reaction of bromide and ozone. Chlorite is a byproduct of chlorine dioxide. And systems have to develop and implement a monitoring plan. So they have to have specific locations where they sample. Typically, these will be at the far ends of the distribution. You're looking at finding the highest concentrations possible. And they have to have schedules for collecting samples, determines how they calculate compliance, whether they have removal requirements, and requires quarterly sampling for disinfection byproducts and reporting of those results to the primacy agency. And that is the state environmental agency in every state except Wyoming. Wyoming has given the EPA primacy, so it doesn't have its own agency. The surface water treatment rule, on the other hand, is applicable to systems that use surface water or those that are a groundwater supply under the direct influence of surface water. The East Lansing Meridian Township system, I'm going to say was because I know that they were in the process of making some very significant changes to their system. Their filter backwash water went out into storage lagoons, actually drying lagoons. And then the supernatant was pumped back into the plant. So the groundwater, saw the light of day. Okay. And that supernatant, because it was pumped back to the head of the plant and because it was outside, it becomes a groundwater under the influence of surface water. And then the surface water regulations impact that plant. So they were looking at some very significant modifications to change their process so that that backwash water did not go out into those ponds. They didn't recycle the water from the drying beds back into the plant. And those are requirements for filters and significant requirements for disinfection. So Michigan State, being a groundwater system, actually doesn't have a requirement for disinfection or disinfectant levels in the distribution system because it's a groundwater system. The lead and copper rule is applicable to every community water system, whether they're groundwater or surface water. And here the system is required to validate whether or not they have optimal corrosion control treatment. So that is the goal. What's used for that is the 95th percentile for lead and copper. Lead must be less than or equal to 15 parts per billion.
The action level for copper is 1.3 milligrams per liter.
Lead's the one we tend to be concerned most with because it's a neurotoxin. In Michigan, this come the first of the year in 2025 will decrease to 12. This is referred to as an action level. If the 95th percentile exceeds that level, then the plant is deemed to not have optimal corrosion control. They have to do additional sampling and they have to ensure that they do have optimal corrosion control. One of the challenges with the lead and copper rule is right here. Everything towards the plant, okay, from the curb stop is public. So everything you're seeing is blue. In the US, everything you see on the service line is the private responsibility. So that makes it much more difficult. The question is, who has responsibility for those lead lines that are typically on the private side? This major issue in Flint. It's actually now an issue in Benton Harbor because they're seeing lead levels that are extremely high in some cases. And the question is, who has responsibility for replacing those lead service lines? In Lansing, all of the lead service lines were replaced. And what happened was the Board of Water and Light determined that the replacement was required as a condition of service. And essentially what they did was essentially took the private lead copper lines as eminent domain, allowed them, like I said, as a condition of service, you had to allow those lines to be replaced. There are still lines in Flint that haven't been replaced, and there's still some people that are unwilling or don't want those lines to be replaced. So looking at what we will do for the next few weeks, okay. Lab 1, you will determine what we refer to as the Langelier saturation index in the distribution system. And as part of that, you will make recommendations to the head of, if you're living on campus, IPF water division. Okay, so it looks like most of you, except for just a couple that are either living on campus or close enough to campus. So those of you in that situation, you will be responding, you'll be doing the study on campus, and your recommendation will be to the head of IPF water division. Those of you that are not, Blaine, I know you're one. If you're not, if you can just put in chat who you are, and that way I make sure that I have that information so that I can make sure that what you're working on is really beneficial to your learning. There will be a graphing assignment. So we've talked about graphing last week. I'm going to have you basically graph some data. I want you to think about how to present that data. And this is really just to help you in terms of data presentation and help you in your reports. And then assignment 3 is going to be focused on making some recommendations regarding flushing residential plumbing to ensure that you're not drinking water that is sitting stagnant in the pipe and could contain high concentrations of lead. So you'll be looking at your own plumbing system for that. If you're in Res Hall, then we'll work with you. Those of you that either have been on campus, are on campus, know that one of the issues on campus is red water. This is actually my cup. I went in this is one early January. It came back, went to go make coffee, and that was the water out of the tap. You've all seen, to some extent, situations like that. So red water is a term used for water with high particulate iron concentrations, and it's due to the release of corrosion byproducts. What you see here is referred to as tuberculation. So these are referred to as tubercles. So basically it is rust on the inside of a pipe. It results in the presence of iron bacteria, causes objectionable taste and odor, stains your laundry, can stain plumbing fixtures, can actually result in leaks in the distribution system. You get pitting underneath these tubercles. and it's often controlled by phosphate addition. Now, we can try to mitigate that by, in the pipe itself, forming a protective coating on the inside of that pipe. So a protective scale. Now, we don't want scale to actually essentially consume the inside of the pipe, fill up the volume so that we don't have flow, but having some scale on the inside of the pipe is protective. So we want water that is neither scale forming nor corrosive, and we don't want water that dissolves or precipitates calcium. We want some sort of maintain some essential small amount of precipitate coating that forms, but not too much. And we don't want water that is corrosive. So it's useful to determine the potential for the scaling to occur and the potential for corrosion. One of the ways that we can do that is what is referred to as the Langelier saturation index. So that is the pH minus the saturation pH. And the saturation pH is determined by the calcium concentration, alkalinity, and a constant. And that this constant's a function of ionic strength and temperature. Now, if the LSI is less than 0, then that water is undersaturated and calcium carbonate will tend to dissolve. So if we have this scale that's formed on the inside of this pipe, that's going to tend to dissolve. If we have an LSI equal to 0, then it's at equilibrium. And if it's greater than 0, it is oversaturated and the calcium carbonate will precipitate. So really what Langelier saturation index does is it's looking at the basically it's looking at how well that water that will precipitate or dissolve calcium carbonate. So it's really a function of calcium. Now, to determine the stability of water, we need to look at calcium, alkalinity, pH, and total dissolved solids. So the calcium concentration here is given, notice, as milligrams per liter as calcium carbonate. So it's 53.65 milligrams per liter as calcium carbonate. We need the concentration in molar unit, 53.65 milligrams per liter as calcium carbonate. We're going to divide by the equivalent weight of calcium carbonate, and that is equal to 1.073 milliequivalents per liter. We need molar units, so we have 1.073 milliequivalents per liter. Calcium is a charge of 2+, so therefore there are 2 milliequivalents per millimole. And that is equal to 0.5365 millimoles per liter, or 0.05365 times 10 to the minus 3 moles per liter. So therefore, what is referred to as PCA2+ or P-calcium negative log of this concentration, and that is equal to 3.27. The alkalinity is given here as 82.3 milligrams per liter as calcium carbonate. We need this in equivalents per liter. So if we take 82.3 milligrams per liter, divide that by, do it this way, 50 milligrams per milliequivalent, and then multiply by 1/1000 milliequivalents per equivalent. Milliequivalents cancel, milligrams cancel. We have equivalents per liter. That is 1.646 times 10 to the minus 3 equivalents per liter. And then P alkalinity is equal to the negative log of this value right here, and that equals 2.784. The C we would get from a table. So we had, we were told that the total dissolved solids was 560. The temperature is 15, so we'll interpolate between 10 and 20 degrees C. So this is 2.545. So C is equal to 2.545. That means, and I apologize if you just give me 1 minute, we finish this. P sub S is equal to P Ca2 plus, which is 3.27, plus P alkalinity 2.784 plus C, and that is equal to 8.60. So the LSI is equal to pH minus pHs. So pH is 9.89 minus 8.6, which equals 1.29. It's positive, it's greater than 0, so it's oversaturated with respect to calcium carbonate, and scale will form. So tomorrow what we'll do is, having done this, we'll now look at how do we plan out this sampling strategy that we'll use. What are we going to measure? How do we measure it? How do we make these decisions? Where to sample? And in groups, you'll start making those decisions. So apologize for going a few minutes over. Happy to answer any questions if you have them.